Now we're focused on 3 levels, but this same idea applies to the larger types as well. But it means that we can do things like, for example, if we have a D word, let's say, we can refer to a word within that D word using the PTR operator. Meaning, for example, we can grab only 2 bytes from that D word, or 1 byte from a D word, or a word within a D word, right? So any of those combinations are going to be possible. Oh, wait, that's third one. Yeah, so all 3 of those are going to be possible. So in general, meaning that we can refer to a smaller portion of something. So word within a D word, byte within a word, and so forth. Or it can go the other direction as well. Meaning it can be used to go the other direction. So things like combining, for example, if we have maybe an array of 4 bytes, we can treat that as 1 D word value. Or if we have two bytes, we can treat that as a single word. Or if we have 2 words, treat that as a D word. So we can do all of those different possible combinations, and it's through this operator that's called PTR. So what it means is that let's say that we've declared in our data segment an array of double words. So this would be under .data, and then this would be later under .code. And so we've declared an array of double words, in this case with 3 values. And now with all of our previous examples, right, we wouldn't, if we wanted to refer to array 2, we would have to have an operator of the same size on the others as the other operand. So things like, for example, move EAX, right, array 2, or array 2 plus 4, or using one of the different operands that we've learned about. But now what this really gives us the ability is, so regardless of what size specifier we declared the data with, we now can work at the other levels using that size specifier depending upon what we want to do. So if we have this, in other words, we have these, these values here, which are all associated with the identifier array 2, which has size D word. And based on the way we've previously been doing things, the only way that we could refer to that would be with, for example, using a register that's also D word in size, such as EAX. But if we want to, let's say, just grab maybe a word within that larger array, we can do that with things like the PTR operator. So the instruction here is move AX, and we know from beginning of chapter 2 that AX is a 16-bit register, because we know that it's the lower half of EAX. And now certainly a statement like this is not allowed, right? We already know that that's not going to be allowed. Or a statement like this, for example, is also not allowed, because ARR2 and AX would be, there's a disconnect there because they're different sizes. But when we start using the PTR operator, that's going to change everything, because we are still referring to ARR2 by name, but we're saying that we only want to grab a word amount of data. So instead of grabbing a D word as we normally would when working off of ARR2, since we said word PTR, we're only going to grab 2 bytes or a word, and then store that right into AX. And so we can think about, the value that's also going to be stored here, but it's based on the usual rules of little endian order. So all that still works the same way here. All that's changing is the amount of data that we're grabbing. But what the PTR operator really is giving us is that essentially some increased flexibility in terms of how we can refer to things in our data segment. So instead of having to, grab an entire D word from array 2 and move that into EAX, we can now work at the smaller level, even though ARR2 itself has size D word. So that's one major usage of the PTR operator, and why it's convenient, because otherwise, right, you'd have to move it into EAX, and then from there maybe work with just AX, right? But this is just allowing you to get what you want in more of a direct way, since in this case we're saying all we really want is 2 bytes as opposed to 4 bytes. And in terms of what's the value that's stored in AX, well, we have to think about the usual rules of little endian order, because it's the exact same idea, except we're only grabbing 2 bytes as opposed to 4 bytes. And we also have to think about the exact expression that we have as the source operand in this case, because what we said was, right, word PTR array 2. Well, one thing we can think about here to help us see what the value is we can first think back to something we've done a lot of, which would be a statement like what we have up here. Because we know that, if we did something like move EBX array 2, well, we know that that's right. The whole idea with that, of course, is that it's supposed to put in the entire first term. So we know that in terms of little endian order, that just like we've seen in the Visual Studio environment, that the bytes are stored in reverse order compared to the way that we write them out. And so we know that in terms of memory, that the first byte would be the 1, 2, right? For example, the 1, 2, and then the EB, and then the CD, and then the FA, and the 0 is not part of the number, since we already have 8 hex symbols without the 0. And so we know it's stored in that reverse order in memory, but we also know that when you grab multiple bytes of data from memory, you always reverse them before you would place them into the register. So that's why in the end, we know that with the first statement here, you would get that whole first D word in the correct order in EBX. In particular, EBX would be equal to that 32-bit value, FACD EB12. Now here, little endian order works in the same way. It's just a matter of grabbing less data compared to the first line. So the first line, which does not use PTR because we're working at the same level as ARR2 itself, meaning the D word level. But on the second line now, we are using PTR. We are working at a smaller level, and that's fine. But we just have to think about, right, the usual rules of little endian order to interpret what exactly is going to be stored in AX as a result of this second move instruction. And so based on that, well, little endian order would say that we have the 1-2 byte first, and then the EB byte, and then we reverse the order of those 2 bytes before we place them in the register. So we're going to end up with, right, the EB12 in AX. And we'll just assume here for simplicity that this array starts at address 0. But so far we've been working with just the first term, but we know that we have this kind of layout in memory. This is going to be address 1 and so forth. And so the idea so far was that when we said, in this case, move AX word PTR array 2, and we're just looking at the first of the 3 terms for now, it still means that since we're saying ARR2 here, right, it means that we're going to start grabbing data from where that array starts, meaning from that first byte, which would be the 1-2 byte. But since we said word PTR, we're only going to grab 2 bytes instead of 4 bytes. So we're going to grab those 2 bytes and then flip the order or reverse the order. So we're going to end up with EB12 in AX. And you know, these operators, such as the the offset operator or the PTR operator, you can also use offsets with those operators as well. So meaning, as another example, we could say move AX word PTR and then some sort of offset also, in addition to ARR2. We'll do that above our memory diagram here. So for example, something like that, perhaps. Actually, CX. So move CX word PTR array 2 plus 2. Similar idea in the sense that we're only grabbing a word or 2 bytes, right? 2 bytes amount of data. But we're just changing where we're going to start grabbing that data from. As we saw up with the statement up here, if we don't have an offset, then it means we're going to start grabbing data from where array 2 starts in memory, meaning because we know that just as you would normally think about an array, right? We know that the name of the array itself refers to the starting address. And because of little endian order, the very first byte is that 1, 2. So that's what AR2 by itself refers to. And so that's exactly why if we say word PTR array 2, it means you're going to start grabbing data from here. And since you said word, we're only going to go to a total of 2 bytes. So we grab those 2 bytes, flip the order, and that's how we end up with EB1, 2 in AX. The only difference here is now we're saying, well, I want to grab 2 bytes, but now I want to change where I'm going to start grabbing those 2 bytes from. Now I want to start grabbing 2 bytes from array 2 plus 2 instead of array 2 itself. And that's fine because we know that if we continue this diagram, it follows that if this is array 2, then the next byte over would be array 2 plus 1, which means the next byte after that would be array 2 plus 2, so on and so forth. So that's fine. So that just means that now with the second statement here, now we want to start grabbing our data from here. And since we said word, it means that we're also going to continue to the next slot over, grab those 2 bytes, and then reverse the order before we place it into the destination, right? In this case, register CX. So now we're going to end up with ABCD in register AX. So we can always choose, in other words, when we're using the PTR operator, not only can you choose what level you want to work at in terms of word, byte, or D word, but you can also choose where you want to start grabbing the data, just as you could do that without using the PTR operator, right? We've, of course, seen many examples of that without the PTR operator, with just using things like offsets. Now we're just combining these ideas together, right? Meaning offset and things like the PTR operator. Oh, question about shouldn't address 3 store FA? Oh, let me. Oh, yes. Yes, that's right. That's right. Last one there was, yeah. Yeah, the last one there was FA. So yeah, 1, 2, EB, yeah, CD and FA. Good catch. Yeah, so then, yes, it's going to grab, in this case, if we do the array 2 plus 2, then it's going to, yeah, it's going to grab those 2 bytes, the CD, FA, and then reverse the order. And same idea, because we might even want to get something from one of the other terms in the array as well. So in this case, both array and array plus 2, right? Both of those we're going to be referring to ultimately a word from the first term, meaning from the first of the 3 D words here. But we can expand on the general idea to also start grabbing things from some of the other terms in the array as well, because it really just comes down to what your offset is in terms of what you're going to actually end up grabbing there. So if we use a larger offset, then we'll eventually start getting into, for example, the second or even the third term. So if we continue our diagram here, so we mapped out the first D word. But we can just continue it. So similar idea, if we start saying things like, for example, +4, well, then we're just going to start getting into the second D word, or the second term from the array. Meaning if we do a statement like this, move dx now word ptr array 2 + 4, well, now same idea, we're going to grab 2 bytes, but we're going to grab those 2 bytes starting here, meaning these 2 bytes at array 2 + 4 and array 2 + 5. And then as usual, we're going to reverse the order. So grab the byte that has the 8, 9, grab the byte that has the 2, 1 hex, and then flip the order and place that in this case in dx. And so on and so forth, right? So if we keep adding, larger offsets, then we'll, for example, start getting into the third term. And so again, that's the general idea, or at least one usage of PTR is to grab part of something. Now you could also grab individual bytes as well from here. And that would be similar, except we would be using byte PTR instead of word PTR. Similar idea. So if we want to do something like move maybe into AL, since that's a byte size operand, and then byte PTR, and then we can use an offset depending upon which byte we want to grab. So let's say that maybe we want to do ARR 2 + 3, so meaning this byte, then it's just going to move that single byte into AL. So that also is possible then, just moving a single byte from within a D word. So we're seeing that when your data is D word, then you can really do both of those kinds of things, right? You can grab, for example, words or grab bytes if you want to work at either of those smaller levels. And the syntax here was just the level that you're planning to work at, meaning that size specifier, and then PTR, and then where you want to start grabbing that data from comes after PTR. Okay, so that's, again, that's one usage. And again, it's a similar thing. If you had an array of words, you could also, for example, grab bytes within that array of words as well. So one usage is to grab a smaller portion of something. So like a word within a D word, byte within a D word, or maybe a byte within a word. Now it goes the other direction as well, though, meaning that we can also use, for example, an array of bytes to maybe form a D word, right? Because if you have an array of 4 bytes, then using the PTR operator, you could grab those 4 bytes together to form a D word. Or if you have 2 words, you can grab those together to form a D word, or 2 bytes to form a word, and so on and so forth. Okay. Up to here. Okay, okay. And so again, it's always helpful to visualize memory, especially when doing things like the PTR operator, because we're getting really specific now in terms of working at these different levels. But it's a very similar idea, except now the difference is we've declared our data in terms of byte instead of D word. But again, the reason why all these things work is because in the end, the data is just data, right? And we know that everything in the data segment is really one big array, right? In the sense that everything is stored back to back. And so all we're really doing when we use the PTR operator is we're just choosing, a certain portion to refer to. But that's why these things are in general possible, because it's just really one big array, meaning the entire data segment. So 1, 2 would be the first byte, and then the 3, 4, and so forth. And we ended it there in that case. But same idea. So if we say something like move EAX, in this case, D word, PTR array 3, where array 3 is an array of bytes, well, that's fine. We're just saying, starting address is array 3. we want to start grabbing data from where array 3 is, which would be this first byte. And we want to grab a D-word amount of data, meaning we want to grab 4 bytes starting from that location. So that would mean that we're going to grab these 4 bytes. And then we're just going to, as usual, we're going to reverse the order. So we're going to end up with 7, 8, 5, 6, 3, 4, 1, 2 in EAX. Or if we, in this case, if we say something like array 3 plus 2, similar idea, we're going to grab 4 bytes, but we're going to start grabbing those 4 bytes from a different spot. So if we say something like dword ptr array 3 plus 2, well, now we're going to be starting here, and we're going to grab the 4 bytes starting from array 3 plus 2, meaning those 4 bytes, and then we're going to reverse the order and place that as a single dword value into register EAX. So CD AB 7856. We do that kind of statement. So that's one example of how we could use this this byte array. So basically take 4 bytes from the array, combine them, form a dword, and then store that somewhere, and then presumably use that in some way. Another thing that you could do here would be to form a word with 2 of the bytes. Is what? Oh, yeah. Normally, by convention, yeah, we have the hex letters in uppercase. Yes. Yeah. So, oh, yeah, that should be yes. Yeah. So by convention, we usually do the hex in capital. There's a couple other examples here. If we want to maybe grab some words from this, we can do that as well. So for example, move into whichever 16-bit register, move into BX. Word, for example, PTR. We do something like that, then we're going to be just grabbing only a word amount of data instead of a D word. So in terms of our diagram, which we'll move down here, if we do something like that with array 3 plus 2 and word PTR, it just means that we're going to grab only 2 bytes and then store that as a word. So instead of grabbing 4 bytes from the array of bytes, we're just grabbing 2. So we get 7856. And so on and so forth. So that's the general idea. Those are both, major use cases of the PTR operator. So it's just convenient in the sense of being able to combine things together, or as we saw before, to refer to a smaller portion of something that's larger. So we'll see this operator come up in some cases. Sometimes when you're working with depending upon the instruction and what the operands look like, sometimes when you're using literal values, this comes up as well. Like if you're doing this would be another case where it comes up. If you're doing something like, add dereferenced ESI, comma 5, that would be another case where you need it, because otherwise it's not going to be clear what size level you're working at. So that's a little bit of a different reason for using the PTR operator. We've looked so far at things like, I want to grab a word within a D word, or I want to combine, multiple bytes form a D word. But another case where that comes up is when we have to be more specific. So, when we have an instruction like this, then we're fine, because add EAX dereferenced ESI. Well, we know what level we're working at, right? Because EAX is a 32-bit register. But remember, ESI could be pointing at anything. ESI itself is a 32-bit register, but it could be pointing at a byte, for example. It could be pointing at a word. It could really be pointing at anything. And we have to know when we write a statement like this, like the bracket ESI, we have to know how many bytes of data do we grab, because ESI is storing a memory address, but we still have to know how many bytes of data are we grabbing from that address. Is it 1 byte? Is it 2 bytes? Is it 4 bytes? We have to know. Now, with an instruction like add EAX bracket ESI, we know that we're grabbing 4 bytes because EAX is a 4-byte register. And that would have to be the case for this add instruction to work, because we know the two operands have to be the same size. But sometimes we may also have a literal value used with something like bracket ESI. So that would be another case where we're definitely going to have to say a little bit more, because we have to make sure that we're not being ambiguous. So here's the problem, right, that we run into. So, and this is assuming, right, I mean, of course, that we already have set up the right address in ESI before this add instruction. But assuming we've done that, the problem still is we don't know how many bytes of data that we're working with. So what does that mean to say add dereferenced ESI comma 5? Well, I mean, it means to take the integer value 5 and add it to that area of memory, that value of memory, but we still have to say how many bytes, right? Because there's, of course, a difference between saying take the value 5 and add it and then go to that byte in memory and add 5 to that 1 byte versus saying take the value 5 and add it to a word or add it to a D word, right? We don't know which of those is the case from the information in the add instruction in and of itself. And because down here, right, there's always two things that you have to know to be able to use a pointer, right? You have to, of course, you have to know the address that it's supposed to be pointing at, right? Certainly that is something that has to be set up. But in addition to that, you also have to know what are you working at? What size are you working at, right? Which is why, for example, in C++, pointers are still type specific, right? You know, there's a difference between pointer of type int star or pointer of type char star or pointer of type double star, right? Because those things matter, right? We have to know how many bytes really are we grabbing, are they working with? So, you know, this kind of thing is going to be a major problem because we don't know that. We have no way of knowing whether ESI is pointing at a byte, a word, or a D word, but fortunately, we can use the PTR operator to say exactly that. So, you know, if the idea is that if that ESI is pointing at a D word, like, you know, maybe, for example, we have an array and we're wanting to do something like add the value 5 to each element in the array. Well, you know, then we could say D word PTR before the bracket ESI, and then that's going to be fine because now it's no longer ambiguous in terms of what we're trying to do. So, but again, it's important to make those distinctions between what, you know, what's ambiguous versus what's not ambiguous, because again, with the earlier examples that we looked at, we weren't using PTR here. Now you could use PTR with, you know, an instruction like this, but we don't have to, right? Because if, you know, it's inferred that if the other operand, it has a known size, which EAX does have a known size because it's a 32-bit operand, then it follows that when we talk about grabbing the data that ESI points to, we have to grab a D word amount. We have to grab, in other words, 32 bits. Because if we grabbed a, you know, a lesser amount, then it wouldn't be a valid instruction since EAX itself is 32 bits. So that, you know, that would be a case where we didn't have to do it. So now that we know about the PTR operator, we can also just make kind of a general note that with an instruction like this, it's really optional, right? You know, you could say something like add EAX, comma, you know, D word, but PTR, but we don't really need to because it's already known. So up there, we don't have to do it, but then down here, we are going to be needing to do that. So now we no longer have any ambiguity, right? If we say add D word PTR bracket ESI, now we know exactly what it is that we're trying to do. So now we're going to take this value 5, but when we go to memory, we're taking that value as a D word. And so it's a 4-byte value and adding 5 to it, as opposed to only adding 5 to, 1 byte only, for example, or only 2 bytes. Or if it's a word that ESI is pointing out, then we could say word PTR. Similar idea to the comment up here, except now it'd be for the case where it's pointing at a word. Or same idea if it was pointing at a byte. So yeah, if we're going to have a literal value, um, if we're going to do something like one of the operands is dereferenced, for example, ESI, and the other is a literal value, then that would be another case where we're going to end up using that PTR operator, because otherwise we're going to have no way of knowing um, which of the cases it's supposed to be. But now we do know as long as we're using PTR. So these are 3 different cases that are going to do 3 different things, just depending upon whether ESI is pointing at a word, a D word, or a byte. And we can just make that clear here with the help of the PTR operator. So D word PTR or word PTR or byte PTR, just place that in front of the dereferenced ESI depending upon which of the cases we are handling currently. Okay, so we'll go ahead and take our break, and then after the break, we'll start to look at loops, right? So your assignment this week will get into loops, and then you'll have some more. Starting next week, you'll have some more advanced looping assignments. But we'll look at the loop instruction after the break. And we'll see things like, for example, how do you do a single loop? Eventually, we'll look at how to do things like nested loops, right? So all the kinds of things that you could think about in C++, we can think about how to do those things in the same kind of way here at the assembly level. So we'll look at the loop instruction and see how the loop instruction works with the help of register ECX. So you might recall at the very beginning of chapter 2, when we introduced all the registers, we said that a lot of the registers had a special name or a special purpose. And ECX was one of those, because we said back in chapter 2 that ECX was the loop counter register. So we sometimes call it the extended loop counter register. And so what we're going to see is that it's used by the loop instruction to control the number of loop iterations. So now that we've looked at a lot of these key things like the offset operator, the PTR operator, direct memory, direct offset, indirect indexed operands, now we're ready to start thinking about putting all these things together in terms of loops, right? So we'll look at some code examples with loops, and we can revisit some of these things that we've outlined here in the Word document, and we can think about how to do them in terms of a loop, right? Because of course, we want to be able to take these ideas like adding up all the elements in the array and being able to generalize them in terms of a loop. So we'll revisit some of these things and see how we can set them up in terms of loops. Okay, question about, oh, that's fine, yeah, if your internet went out for a second. So we're basically adding 5 to an int after dereferencing. Yes, with the first one, yes, because dword we know is like type integer. So yeah, with the first one here, that's basically, yeah, what you're doing. Yeah, if you think of it as like an integer value, meaning a 32-bit value, yeah, you'd be getting that 32-bit value from memory. Because remember, this is really a memory operand, even though we're using ESI here, since it's ESI inside the brackets. So you're getting that integer from that integer value from memory, and then you're going to add 5 to it, and then it's going to be a different value. So that's what this one here is doing. This one, well, this would be like short integer, for example, in C++, right? But 2 bytes. Similar idea, but this is grabbing just a word and adding 5 to it. And then this is grabbing just a single byte from memory and adding 5 to it. So all 3 of those things are in general possible, which is why we also have to use the PTR operator just to make that more clear. No. Well, yeah, when we talk about, I mean, we can think of all data really in the end as numbers, because we saw before that everything is really just a binary number, right? Even characters or strings are just numbers because of the ASCII code table, where we saw, for example, that the character capital A was 41 in hexadecimal or 65 in decimal. But the difference is just in terms of the size, really, the number of bytes. So we can think of the first one as kind of like an integer in the sense that it's 4 bytes, which is also the size of, usually it's size of an integer in C++. Now they're all doing a very similar thing in the sense of adding 5 to a value from memory. It's just a matter of, well, how big is that value in memory? Is it a 4-byte value, which would be the case up here? Is it a 2-byte value, which would be the case here? Is it a 1-byte value, which would be the case here? Right, because in general, all of them are possible, right? Depending upon how exactly we are using ESI in the current moment. Because we could, throughout the program, we could have ESI point at any of these, right? Any of these variables that we've established in the data segment. So for example, here, you could move ESI offset value 3, right? Which is a D word. So now you have the value 3 as a D word, as a 32-bit value, and you're going to add 5 to it and store the result as a still is a 32-bit value. So 8, assuming we use 3 here, then 8 as a 32-bit value. Or we could move ESI offset value 2, which up here value 2 was a word with the value 4. So that's fine. That just means that we're going to be storing the sum of that, or 4 and 5, which is 9, but we're storing the number 9 as a 16-bit value at value 2's location in memory, right? So now value 2 would be 9, right? For example, and value 3 would be 8. Or I'll move value 1 into, because value 1 up here was a byte. So move, value 1's address into ESI, and then do add byte PTR ESI. So the idea also this time is the other difference with this one is now we're using, now the PTR operator is on the destination operand, right, instead of the source operand. With the previous examples, it was on the right side, meaning it was the source operand. So memory wasn't changing when we were doing things like move AX, comma, word PTR ARR2 plus 2. But now memory is changing since the memory operand is the destination operand. And then in this case, the source operand is just a literal value. Or you could also use a register as the source operand too. But here we needed that PTR operator since the other operand was just a literal value. So then with the third one here, yeah, we'd move the address of value 1 into ESI and then add 5 to it, but it's only a byte, right? So that'd be, 2 and 5 or 7, and you'd be storing 7 in value 1, right, as a single byte. So that would be the result of all of these instructions here. So again, we can always change what ESI is pointing at, right? It can point at a word, it can point at a D word, it can point at a byte. That all those things are possible, and they can all change throughout the program, potentially many times, right? Change throughout the same program. And that's fine as long as we're correctly setting things up. So it's fine to, do all of these things back to back as long as we correctly use the, in this case, the PTR operator to help us do that. Mm-hmm. Mm-hmm. Yeah, so these are changing, yes. So yeah, so we can all add a comment here. Value 2, that was the one that was 4, so that's going to be 9 as a word. And then value 1 is 3. So it's going to be 8. So yeah, in this case, we're actually changing memory, right? So we can also have the PTR operator show up on the left side as the destination operand as well. Okay.